Welcome everyone to this week's webinar of the International Neural Networks Society. And I'm really excited about this. Last time we spoke about education, and there were many different topics already. In the future, we will speak about governance. But we are actually handling or covering a wide spectrum of AI. And this one here will become very technical, but the topic is very highly motivated. As you might know, all of these large language models or other AI technologies are requiring more and more compute. And this is just an example of a graph of the past development, but also the future prospects how AI will maybe require, what kind of a compute it would require in the future. And you see it's not just linear, because the y-axis is already exponential, but it's not only exponential, it's also hyper-exponential. And these things have been seen in the recent past, but are forecasted also in different scenarios for the future. And one of the reasons is, we tackled that already earlier, that these large language models require a lot of compute and are really big, have a lot of parameters. But sometimes, depending on the tasks you have, small models can do the job very well. And I'm not the biggest expert at that, but in a moment we will hear more about it. The general approaches are, for example, distillation, where we have large models training their knowledge or giving their knowledge to smaller ones, or pruning. That can be on different levels. We will hear more about that in a moment, where the models will be just made more tiny, or even the data which we are using. And that all will contribute towards the sustainable deployment of AI. And a great speaker of that is someone who was really heavily active in that environment, and that's Zhui Zhu. He is joining us from Singapore today. He is a deputy director of the A-Star Center for Future AI Research, and he is also the technical coordinator of one of our INNS section, the AICI section. So he is really the best person here to speak about that today. He also won and has been nominated for many best paper awards. And to even further underline his activity, he is just this year, already PC chair or associated PC chair in 2 major conferences of the society. So that active person has really a lot to say. So without further ado, let's hand over to Joey. Please, the floor is yours.
Okay, thanks for the introduction, Marcus. I'm going to share my screen. Are you able to see my screen?
Yes.
Okay. Yeah, it's I'm very pleasure to give the talk about our recent research work on this topic, dataset pruning and distillation. I think it's quite important. So I will start with the motivation, and even though the Marx have a very good illustrative example why we need dataset distillation and pruning. So there are 4 reasons why to answer this question. The first one is increase the model size. The early size already mentioned this. The second one is the massive training data. So in order to train the big models, we have to use the more and more training data, so increase all the way. So of course, with the more and more training data and increase the model size, of course, will result into the exponential increase in cost for the model training and the evaluations. So last part is about our environment. So I also see the model training and for the large language model, for example, the GPT-3 here is millions larger compared to the round trip from the New York to from Singapore and New York. Also, can produce a much more carbon emissions compared to the U.S. car for the whole lifetime. So that's 4 reasons drive us. We must study how to make the data set smaller and without sacrificing too much on the performance. So our ultimate goal for doing this task is to make our AI more sustainable. Okay, so I give you more concrete examples to illustrate why this task is so important. For example, suppose the original data we have 50,000 images. Let's say CIFAR 10 actually. We have the 50,000 images. So by condense or by making the by learning a small synthetic data set, let's say we just have the compact image around 500 images, right? By doing so, what kind of benefits we can have? First is about the data storage. Suppose the original one, if we need a 100% data storage for store original data set, but after comprising, after distillation, we can only need 1% of the data storage. The second one is the training speed. So we can speed up more than 10 times. The last one, actually, this motivation brought by one of my collaborator from HPE. So actually, for HPE, the whole company, actually, the evaluation cost is huge. It's around 100 millions. But they suggest that by applying this data distillation or dataset pruning methods, actually can reduce the evaluation cost from 100 million to less than 1 million. Of course, after distill the data, we generate the small synthetic data. Then we can use the synthetic small data for evaluation, as I mentioned, and for other settings, for example, federated learning, continuous learning. So dataset distillation is very important. The distilled data can be used for many scenarios. That's quite important. So the question is how to distill the data, how to make the data set from original large data set to a very small one. There are 2 ways to do that. The first one is the dataset pooling. So the key idea is that we select the subset of the images from the original full data set, very large one. Without the performance drop is our final objective. So the other way to make the dataset smaller is the dataset distillation. So you can see we use a different verb. We use the verb learn here. So the first one, and the pooling is about the select. The distillation is about the learn. We're going to learn a few synthetic images because we learn from the render images and become more meaningful images. Right? Of course, we have to change the image pixels such that the synthetic images can replace the original full images for different downstream tasks. Okay, I will introduce one by one. First, I will talk about how to prune the data set. Okay, dataset pruning. Sometimes in other papers, they use the other terminology, for example, the subset selection, but actually refers the same task, machine learning task here. So this is the figure shows what is the dataset pruning. So suppose this is a full data set. To select the representative data points from different classes to construct the core set. So sometimes we also say it is core set selection. So the objective is to select the sub images in the full data set without the performance dropping. Okay, so for example, this is a CIFAR 10. Applying the different algorithm, dataset pooling algorithm, we can select those images. Okay, this is examples of the selective images. Okay, so the core part, the core technology about how to select the dataset select the data points. So the very important thing is how to set up the metric. So the metric should tell us which data points is more informative, which data points are more important. So this is the milestone paper to set up the metric. Okay, so the metric is called forgetting. So they have done the experiments and observed there are two phenomena. The first one is that some samples are consistently forgetting across the subsequent training, but some samples are never forgotten. Okay, so the very straightforward way is that we're going to approve those unforgettable data points. So this is the definition for forgetting statistics. The sample I undergoes a forgetting event when it's correctly classified in the current update, but misclassified in the next update, which means that this current data points cannot memory the knowledge. So that's why they're suffering. We term this kind of phenomena as this data point is suffering the forgetting event. Okay, so this is the pseudocode for how to implement this idea. Very simple, right? This is the sample I from the previous accuracy for sample I in the previous update. This is the current update. If the previous accuracy is larger than the current accuracy, then we add 1 to this ticker. This is the ticker. So this is how this ticker helps us to compute the forgetting statistics. How many events how many forgetting events they are going to experience during the whole training process for each individual data points. So after we get this ticker, the numbers, the values, we're going to do the sorting from the largest to the smallest. So according to these sorting numbers, then we're going to approve those unforgettable ones. Okay, this is a ticker to record the number of the forgetting events for the sample I. Okay, let's see the simple experiments results. So there are 3 data sets. From the left to right is the meanest, permitted meanest, and CFR10. So the difficulty of these 3 data sets is from left is the most easy one, the right-hand side is the most difficult one. So what we can observe is that most of the samples, no matter which data set, most of the samples actually are unforgettable. That's why it's the long tail shape, right? So the second observation is that more complex data set contain significantly fewer unforgettable samples. That's why this is to be shorter compared to these 2 easy data sets. Okay, so when we set up the benchmark evaluation experiments, there are 2 baselines we have to compare with. The first one is we don't remove any data points. This is the original data sets. So this is a baseline we want to compare with, right? So the other baseline is that we're going to randomly drop some data points in the data sets. So we can observe that by using the forgetting metrics, we can the performance drop very slowly, right? So which means the forgetting metrics is playing his job in selecting the most informative data points. Okay, this is the visualization results. So based on this metric, forgetting metrics, this is the most forgettable samples. So we can see the visual pattern is very clear to human beings, right? This is the most forgettable samples, okay, which means that these samples has experienced the most forgetting events. So these images actually to our human beings not easy to give the labels, right? We can also name this kind of forgettable samples as the difficult samples in this data set. So in other words, we can say forgetting metrics also match also with our human visual perception. Okay, Okay, so forgettable samples seems to particular and uncommon features. Okay, well, what's a challenge for forgetting metric? So one challenge is that the collection of the forgetting statistics for large models is time consuming. We have to go through the whole training process, right? But if we're going to compute these forgetting metrics values for very large models, so it's very time consuming. How can we resolve this issue? The very simple, straightforward solution is that we can select those data points via the proxy. So what's the idea of the proxy? We can use the smaller proxy network with a fewer epochs to speed up the training process. So compared to original methods, we go through the training from epoch 1 to epoch 100, right? Or possibly just use the 10 or 20 epochs. We want to do experiment to see whether we can still select those informative data points. Also, for example, we can use the shadow one, but with the similar architecture, can we also use the smaller proxy network to select the same data points? So this idea is very simple. It's called a selection via the proxy. Let's see the results, whether it's possible. So this is the full data set, right? This is the baseline. There's another one randomly dropped, right? Now this is the baseline from previous methods for forgetting metrics, right? So suppose the backbone we use the ResNet 164. So if we just use the ResNet 56 and the 5020, ResNet 20, can we still can achieve the comparable results? From this result, we can see the error and in other words, the accuracy almost the same, very comparable, right? So which means that we can still use the smaller proxy network to replace the original large network to select the data points. Okay, so performance on par with the large network. Okay, next, collecting the forgetting statistics. Of course, still needs the complete training, right? No matter the other way to solve this one is the previous method is going to use the proxy network. This idea is the total difference. They come up with new metrics to measure this forgetting or difficulty of the data points. That's called the error vector. I believe all of us are familiar with this metrics, but actually it's the very first time to use this error metric to select the data points. So, that's very important. We should use the early stopping strategy. So for example, we just use the 20 epochs and the error vector score and average over several with initialization. Because even with the initialization, random can make the final results very random. So that's why we should run these metrics many times that take an average. Okay, this is the mathematical formula. So this is the last layer, largest vector. This is the one hot label. We just compute the difference, the error between these two. So what can we do with this error vector? So we're going to prove the samples with smaller error vectors, all right? So smaller error vector means the easy one. So we're always going to improve those easy samples and remain those difficult samples. This is the other way that we come after the metrics, right? So this is called the error vector, which is very different from the previous two methods called the forgetting events. So error vector, we don't need to record the forgetting events through the whole training process. We just use the last layer, then do the computing for the error vectors. Okay, let's see how is the performance for this new metric. So this is the no pruning for the purple line. For the red line is the randomly pruning. Okay. This is the forgetting score. This is the original line is the forgetting score. This is the error vector. We can see the performance, right? Very similar, right? Very comparable. Okay, so comparison of the forgetting scores at the end of the training and error vector early in the training. So in this case, we can see the performance is very similar, right? So which means also suggest that this metric is also a good one, well, also good an alternative to do the dataset pooling. Okay, there's some problems for this error vector as well as the forgetting events. So that's with further do experiments that found out the sample importance scores fluctuate the epochs. The sample importance scores can be the error vector, right? So leading the from this figure, we can see the distribution of this core set, the selected data points, and at epoch 10 and the epoch 100 are very different. Okay, at epoch 10, the selected data points, a whole data set actually congested in this corner, but for 100, the selected data set actually spread over the whole data points. So if we use the early stop criteria, may have some issues. So, but if we swap, we change the other data set, we found the distribution is the opposite one. At the epoch 10, maybe contrasted in this corner, but at the epoch 100, will be spread over. So it's quite a data set dependent. So that's observation we call is the fluctuation of the core select distributions. How to resolve this problem? So we introduced these methods called the temporal dual depth scoring, which we published CVPR 2024. The formulation, the original formulation is that this is the original data set. Okay, we call it the GU. This is the selected one. So subset. So we're going to minimize the difference between these two and only compute the last layer, the activate functions. Okay, so but as I mentioned, right? So different epochs, actually the selection of the core set varies a lot. So we have to consider the training dynamics. That's why we take the average around the past 10 epochs. That's how we consider training dynamics when we constructed this metrics. Okay, so let's see the results. Okay, this is forgetting metric. Most commonly used the baseline. Also, is the best competitors. You can see the performance around this 77.5 accuracy, test accuracy. And our proposed method TDDS actually can perform much better, right? And we choose the different parameters. Okay, so further, we're going to apply this TDDS, this concept to medical images. But the medical images compared to other C410 or images, there are two very special, unique characteristics or observations. So medical image, they said present fine-grained intra-class variation. So this is the class 1, that's class 2, class 3. But but for each within the class, actually, we can see that the visual features are quite different. Okay, I mean in terms of the original pixel level. Okay, so so that's called the intra-class variation is very huge in medical images, but inter-class similarity. This class actually and this class are from different class, but they looks very similar, right? These two classes looks very similar. So that's called the inter-class similarity is very high. So different, as I mentioned, different from the common objective classification, this traditional computer vision task, this medical image classification task is quite challenging. So which also posed a unique challenge for this task here, dataset pooling. So what we further do experiments and found that if we apply the deep learning methods, different layers actually exhibit the evolution nature from the simple to the more complex stages. This is the visual feature, how it looks like, I mean, across the different layers. That's the evolution nature in the space domain for different layers of the architecture. The other one is from the temporal domain, okay? So importance of the samples in enhancing the model performance, the varies across the different training epochs. For each data points, for example, these data points in the early 20 epochs, the sample importance is very high. But when the training process goes on, the sample importance drops significantly. Sometimes it goes higher again. So varies a lot. It's very unstable, right? So there's two challenges for these medical images: the training evolution and the epoch level fluctuations. We should consider both two challenges when we design the proper dataset pooling for medical images. Okay, then we propose an evolution aware variance, this matrix for the medical image dataset selection. Okay, and this paper was published in 2024 ACM Multimedia Conference, also nominated as the best paper award. Okay, so how to capture the training evolution? The idea is very simple. We set up a dual window, two windows. The first window, we capture the training evolution, training dynamics from the early approach and to late approach. We also set up another window, so from the end of the epochs to the early epochs. Okay, so as I mentioned, right, the early epochs and the later epochs actually they will select the different data points. So what we should do is that we take the intersection, okay, of the two selection results. That's called the selected core set. We can also use the name the core set in core set selection. Okay, this is the core idea. Okay, so next part about how to do the dataset distillation. Let's do a quick recap. Compared to with the dataset pooling, the dataset distillation is we're going to learn the few synthetic images by altering the image pixels to replace the original full dataset in large scale. But what is the definition for the dataset pooling? Is we're going to select, right? Select. We don't change any pixels. We just select from the original dataset. But still same, we don't want to expect any performance drop. Okay, so learn this is the synthetic images. We can observe the synthetic is quite different from the selected images, right? Now this visualization shows that, for example, the plane here, right? We can barely see their plane patterns. Okay. This is a bird. Actually, we just give these images to the human to a namer, and name person actually cannot tell this is a bird, but the machine can tell the difference between the different categories. That this is supposed that we just condense, we just learn one synthetic image to replace the whole class. This is the results. Okay, see. So from this angle, we can observe this as actually synthetic images is quite different from original images. So the way the machine perceive this information is quite different from the human. Okay, so that's why machine can still tell this is for plane, this is for dog, this is for frog, right? But the human cannot understand the word. So that's why recently I'm thinking about the theoretical foundation why the dataset distillation is work. Maybe for each individual pixel, right? Not all the pixel counts for the discriminative power for the classifier. And that's why another direction called adversarial attack, right? We're just changing a few pixels, we change the class or category for well-trained classifiers, for the deep learning classifier, right? So in other words, we can say maybe in the a few pixels in the original images matters a lot. Not all the pixels are very equally important. So that's also give another view why the dataset destination is working well, right? So because for each individual image actually has a lot of redundant pixels, so cannot contribute too many information to classify training. Okay, so the key difference is whether the pixel are learnable. If unlearnable, it's called dataset destination. It's not unlearnable. We're not going to change any pixel. We call the dataset pruning or selection. Okay, how to formulate this problem, dataset destination? Sometimes in other works they call the dataset condensation, but the core idea is the same. So the objective is to learn the synthetic images to replace the full data sets. Okay, so suppose we have the n images, so it's millions, scale of the millions. We're going to condense this, or we're going to distill this very large n to a very smaller m. Smaller maybe, and the m maybe just a 10, just 20, just 50 at most. Okay, so how to construct this mathematical formula for this machine learning task? So this very straightforward way is to form this problem is that this is the target, this is the original large image data set. This is a synthetic one, this is a smaller one, right? So we're going to do the dataset destination to learn this yellow column. Okay, after learn, we fit into synthetic images and original target images, original full data set into the same neural networks. We're going to generate a loss. So how to ensure that these learned images can simulate some very important properties in the original data set. So we want to minimize want to minimize the loss, minimize the loss between the synthetic images and the original images, right? Minimize the loss. In such a way, we can learn the synthetic small data set. Okay, this is the first paper idea. Okay, but what's the drawback? So the drawback is that even though we can enforce the loss of these two data sets actually is very small, sometimes even close to zero, but we cannot guarantee these synthetic images can be used for replace the original images, because a loss cannot represent the characteristics, the features, the meaningful features for these synthetic images, right? Just like walking through different destination and from the original points, but the final destination, we have to share the same final destination. That's called a loss. Doesn't guarantee actually we can these two robots actually are the same robots, right? They still can be far away at the starting point. So how to guarantee, how to impose the more constraint in this learning process? For example, we can constrain the gradient matching, okay? Because the gradient generated in different layers, right? We can constrain the gradient between the synthetic image and the original image as small as possible. The difference as small as possible, right? So which gives the more information, just compared to just constrain the loss, the final layer, the loss as small as possible, loss difference, right? What other constraint we can impose during this learning process? We can use the distribution matching. So what's the difference between the distribution matching and the gradients? So gradients is very tight with the very relevant to the architecture, neural network architectures. If we change neural network architecture, the gradients will be totally different, right? So, but that's something we want to avoid. Once we learn synthetic images, synthetic data set, we want to hope the synthetic one can be generalized to different architectures of neural networks. Cannot be always tied with the particular architectures. So that's where we should avoid to use the gradient descent matching. So that's why we can use the distribution matching, right? So distribution is less dependent on the architecture, even though there's a little bit dependent on the architecture, but compared to gradient descent matching, actually is much less dependent with the architecture. Okay. What else constraint we can impose here? We can constrain the trajectory or parameter matching. Okay. So in this we can consider the training dynamics during the whole training process, right? So this is from the temporal domain. We can impose this constraint to ensure the synthetic image can mimic all the behavior dynamics, training dynamics of the original images. Okay. So, but all these four methods just I mentioned, right? No matter the loss constraint, the gradient constraint, and the parameter constraint and the trajectory constraint. Of course, the trajectory one matching gives the better performance. Okay, but however, trajectory error still exists. This animation shows why. In the training process, the true trajectory starts from the same point. Okay, we want to minimize the difference between these two data set, right? This is the static one, this is the original one. So impossible, usually in practical, we should break down the training dynamics into the small segments, okay? Otherwise, it's too difficult to do the trajectory matching. Always the long trajectory will always segment into a subsequence, okay? But for subsequence, we want to minimize the difference, okay? But however, in testing phase, the trajectory is studied under different data points. That's how the trajectory error is accumulating all the way. Okay, so yeah, in a nutshell, in testing, trajectory will not be vanishing, but accumulating errors. So to solve these problems, we'll propose to minimize the accumulated trajectory error to further improve the trajectory matching loss for this type of dataset destination, which is published to CVPR 2023. This is the trajectory errors, right? The gap between the training and testing results in the accumulated trajectory errors. We formulate this as below. This is the original initial error. This is called the matching error, okay? At different segments, starting from different segments. So this is called the matching error. The second error we call is the trajectory error. From different starting points, we're going to do the trajectory of a trajectory further contributed error. That's accumulated. Trajectory error will accumulate all the way, okay, in the testing phase. So we're going to minimize the trajectory error, okay, in this work. So later on, we'll also find that no matter which methods for destination, dataset destination, they always follow the sequence in this way. So we randomly select the subset of the original data point from original data set, and we do the matching. Can be the parameter matching, can be trajectory matching, no matter how. We always the randomly sample subset of them. Okay, and we learn the destination. We learn in sequence way. That's how we do the matching for destination. And we always the data is sequence in our original data set. Okay, so but through experiments, this is the results shows that the standard deviation of the predictions. We can, from this figure, we can easily regroup the original data set data points into three groups, major groups. The first one is called the easy one. The prediction accuracy is pretty high, and also the standard deviation is small, which means that we are very confident in prediction for those easy samples. But the problem is that for the medium one, actually the standard deviation, or a lot of the uncertainty in prediction, right? That's what we see very this median data points as subset actually has the largest data standard deviations. Also has the largest uncertainty in predictions. For the hard one, actually the accuracy is quite low, but actually for the standard deviation is very small, which means that for this data point, actually the deep learning architecture is very confident to make a wrong prediction. Okay, so simply regroup the origin data points, by me and the standard deviation, we can visualize the properties of the origin data set. How we leverage this easy, medium, hard subset of the data points. So the idea is very simple, right? So we should, because as I mentioned, all the data destination method is going to we're going to learn the data in a sequence. So we should at the beginning we should use the easy sample to learn, and in the middle, we should use the medium sample to learn, and the later phase we should use the hard samples to learn, to guarantee the training accuracy is increasing all the way. Okay, so that method is called sequential matching methods. Okay, so as I mentioned, the idea is very simple, right? We just regroup the methods into the 3 subsets, and we let the distillation process goes from the easy to medium to hard, to ensure that the training process is more consistent. Okay, more recently, occasion they proposed the method destination formulation in this way. This is for the classification classification error for synthetic data set. This is for the batch normalization matching loss. Okay, they want to minimize the batch normalization layers between the origin dataset and the synthetic dataset. However, distilled data is clustered and central. Okay, this is a state-of-art methods. But the ideal case is we should let the distilled data cover the whole feature space, right? So how to ensure this diversity? Okay, we should further decouple the batch norm loss and emphasize the variation loss only. So this we just simply change the second part of loss, the batch normalization loss, by introducing additional parameters that called lambda variance here. Okay, we simply do the experiments. We found that we change these parameters. Actually, the original methods, we simply set this parameter as 1, but we found that we change these parameters, we significantly boost up the performance. For example, in this data set, this experiments, we found that the lambda should be set as 11 times 0.01. Okay, so which means that by control this parameter hyperparameter, we can decouple the variance, okay, by introducing more diversity when we distill the data set. Okay, more recently, we found another way to improve the data set destination is that all the previous introduced methods based on this paradigm, this assumption is the one instance, the one class. So how they do the data set destination for each individual class, they conduct the data set destination independently. Okay, this is class 1, class 2, class C. Okay, they conduct the data set destination independently without communicating with each other, without sharing information among different classes. So in this work, we're going to break these class barriers. Okay, and for example, so suppose this animation shows the original all the existing distillation methods. We found that the distilled data features actually conjugate into the center of these classes, which means that we were going to produce, we're going to learn duplicate the inter-class features because always central, the feature always central in the middle of each classes. The second, that results into efficient utilization of distillation budget. The second one is that we cannot cover the different cluster, right? So only in the central. So the second issue is has the oversight of the interclass features. Okay, so which results the pool generalization in complex and ambiguous scenarios. Okay, so which results in poor performance evaluated on the validation data sets. There are some ambiguous scenarios between them. So how to resolve this issue? We have to break in the class barriers, and okay, that's how we do. For each synthetic images, we're going to decompose into two subcomponents. The X is the class independent one, and U is the class dependent one. So in this way, we can allocate more budget, destination budget for those class dependent one. But for class independent one, Xi, right? We are going to allocate less destination budget because we have already breaking the class barriers. All the information will be shared. Okay, so we have the more efficient way to distill the class independent Xi. Okay, this is the optimization formulations. Very similar to previous methods I just mentioned earlier slides. The only difference is we do the decoupling, okay, feature decoupling by decompose the synthetic images into class dependent one and the class independent one. So in this case, we are going to learn more information. Right? We share the information among the different classes. All right, data points of the different classes to learn the better X. And we're going to allocate the more computation resources and the budget to learn to increase the diversity for the UJ, which is reserved for the interclass feature. Okay, so this is the final results. We found by such a decomposition by breaking class barrier, we can further boost out the performance compared to the state of art. Okay, better performance, also a higher compression ratio. Okay, this slide shows the recently published paper in this domain from our group. Okay, that's all. And this thanks again for this great opportunity to introduce our recent work. Thanks to the INNS Society for the sponsorship for this webinar series. I'm happy to take any questions.
Thank you so much, Joey. Yes, and as usual, we have time for questions. And I'm really curious. I see some people are also joining. It was very nice to see that the audience is increasing during this webinar. So any questions?
Yeah. So Jay, thank you very much for this insight and how to handle data for better enhanced training, efficiency, and so forth. You mentioned, like, you can have these three groups: easy, medium, and hard. And I think in one of your slides towards the end. So how does one categorize data as easy, medium, and hard?
Okay.
What kind of metrics or cost functions do you use to categorize them?
Okay, I think, for example, in this figure, we shows that we can simply use the classification accuracy. right? Also, we found that this kind of how we divide the easy, medium, and the hard is also related to the standard deviation. Higher means the
so this is based on after you have got the classifier, right?
Yes.
Once you have the classifier based on performance, you can say this about the data, but obviously it's a catch-22, right? How good is the classifier depends on how you have actually developed the classifier. So if you have a great classifier, what might be hard maybe in the medium, but if you have a poor classifier, something that isn't easy for a good classifier might be in the hard. So again, it's very subjective of how to classify. If there's a method that we can use to classify the data prior to developing the classifier, and I think that would be great. But I know this is looking at the classifier and then trying to classify the level of the difficulty in the data, right?
Yeah. Agree. That's good point. It's more like the chicken and egg problem, right?
Yeah, catch-22. Yeah, chicken and egg problem here. Yeah. So yeah, that is only my, we have, different kinds of classifiers with different accuracy and so yes.
Yes.
Maybe
Maybe
a hierarchical approach. You have face step 1 or stage 1 and then use the stage 1 to do the stage 2. Now maybe this could be stage 1 and say, oh, look, that part is the hard data, but now can we focus on the hard data in stage 2 or something like that, maybe in a step-by-step, stage-by-step.
Yeah. That's good suggestion. Yeah, hierarchical way, or sometimes even the simple, we take an average of the different classifier, maybe we'll do. But we try different classifier, and the shape actually remains similar. But as we mentioned, but not exactly the same, but the shape always looks like the banana shape, right? Yes, maybe we can do the simple average or hierarchical way, maybe other heuristic approach will do. Yeah, that's good suggestion. Yeah.
Thanks, Jay.
Thank you, also. And by the way, if someone has a question, just use the raise hand function in Zoom or text in the chat. I see that people appreciated your lecture, and just want to mention the lecture is recorded already and will be available online on YouTube in a few days as usual. So you see also the previous recordings of the previous webinars online, and this one will also be available. We got a new question. Please, Pilar.
Hi, can you hear me?
Very well.
Yeah.
Hi, thank you for your presentation. I am wondering how when we have a classifier which is worked with the specific kind of hyperparameters, that ones that are always very difficult to define as the learning coefficient of learning. If we train a classifier with a specific hyperparameter, and now we want to train the same one again, but using less data, that is going to affect the behavior of the learning by itself, because now we have less data. But I don't know, is that something important, or it's just that you have now to train the classifier, but using another hyperparameters in the learning coefficient or things like that?
Okay, that's a very good question. Actually, when we do this topic, we hope our learned data set actually can generalize a different architectures or similar architecture with a different hyperparameters. But unfortunately, it's pretty tight with how we set up the parameters and the architectures. So yeah, we have to learn again. We have to learn again. Yeah. Also is a piece of art how to tune these parameters. Yeah.
Okay. Thank you.
Yeah, I believe this kind of the topic is still gap between the we hope and the reality.
That's true. Thank you.
Okay.
Maybe then I should not ask my question, but I had one in mind, which is more related to the reality. But it could be, I'm not sure. I really like this kind of approaches. And as you know, I'm also interested in sustainable machine learning and so on. And this dataset distillation is generally really a great idea to work to that. But I'm also typically curious about research and bias, and that we want to have, representative data and support minorities. And if you like a bird or a frog looking different than all the others might be removed very quickly or forgotten very quickly in your approaches, while this individuality is typically quite interesting to keep in the data set. Can we, is there some research trying to control that? Is this also Noggle with trying to control that we keep variation or even diversity in the data sets?
Yeah, Marcus, that's a good question. So I think this dataset destination, even though our ultimate goal is that we're going to condense this or make it this smaller data set, but actually we're talking about loss, right? If we want to do the classification, the loss will be cross entropy loss. We'll minimize the difference between these two cross entropy loss. But if we are talking about the bias or safety or robustness action, we can add on additional source of for different functionalities, right? I think it's possible. Yeah.
That's great. No, this is how I was assuming it to happen, but it's good that you confirmed that. But is there research going on trying to show that?
There are a few research they try to incorporate the more losses of the different functionalities, safety, bias, and the robustness and so on and so forth. Yeah, there are a few, but there are not too many actually. I have to say this optimization framework is quite generic. You can do a lot of things. In nature, actually, data destination is the data synthesis. Yeah, even though we can possibly use on the top of this one, we can use the foundation model to generate the new data set. For example, you use a GPT-4o to generate this one without us learn all the pixel from scratch, right? Or possibly can do that. Maybe we just use we can replace these two by prompting loss. Maybe that's a future direction we can explore.
Any further questions in the audience? I see we're approaching the hour and it's Friday. For some, it's the beginning of the day, but for others, also the end. So I think I will do a conclusion, but Joey will be around for afterwards if you want to ask some other questions which might be not good enough for the recording. Just stay online. I will conclude the sessions. First of all, one more time, thanks for Joey. You did really a well job. Yeah, don't have
thanks.
Physical applause here possible, but I see the reactions of people. They're very happy. Now I will do again that one. And thanks everyone for joining that webinar. And we will have quite a few webinars planned already in the near future. And I give you an overview of that. But to always be up to date, join INNS, have a look on our upcoming webinars, and you will see many more which are coming in the future. First of all, on the 1st of May, that's already roughly in a week from now, Pierre Baldi will give the Gabo lecture, and that's a really great event. I know for some of you in Europe, it's a holiday, the 1st of May, including me, but I am definitely very interested, not only in the Gabo lecture itself, but in the lecture on the AI-driven hospital of the future and beyond. I'm really curious to see what is the latest state of the art in this area. And also very exciting, it has been just confirmed now with the date and time. The time of these webinars so far is, by the way, always the same time slot as now. It's a UTC 13. On the 5th of May, really mark that in your calendar and share it with your friends, because this one will be the Regularity AI webinar, and there will be several speakers. We'll soon also release the names. They're very high-profile speakers from the European Commission, and they will speak about the AI Act, perspectives for the technical and scientific communities. And the cool thing about that is there will be various perspectives of a few speakers, very up to date, but then also a lot of space for interaction. Will be a 1.5 or even 2 hour long session, which we reserve in our calendars, and definitely worth to already mark in your calendars. And already confirmed is on the 12th of June, we will have the Helmholtz lecture, which will then give the latest updates on research on perception. It will be Terry Senofsky, who has received the award already 2 years ago, and he will speak about the research on perception. His title will be soon updated as well. So as I mentioned, join our website, have a look at the upcoming webinars, join INNS, and if you can and really would like to physically give the applause and physically discuss with our speakers, join also our IJCNN conference. Still possible to register for that event. I am personally coming there, and many of the people who are here speaking and joining online today. Join INNS and join our next conference. See you there.